Okay, guys, chapter 2, we are continuing on chapter 2. Chapter 2 will continue about the structure of the atom itself. As you can see here, Rutherford experiment came up with this conclusion. So this is not Rutherford. Rutherford did not really mention anything about the neutrons. That's not Rutherford. Rutherford came out to the protons and electrons. See, and how you can visualize an atom. An atom is an empty space. So you can see here all of its empty space made of central particles located at the middle of the atom itself, called nucleus. So this is here nucleus. This one here. This is nucleus. This nucleus made, Rutherford said, protons, positive charge. And outside, those outside there, those are negative charge particles called electrons. So that's Rutherford. Then another scientist came in and then discovered later on, neutrons are discovered. Neutrons are at the same time. Because when they started doing the atomic mass, it did not match with the Rutherford findings. So it's missing something there with the mass of an atom. So therefore, later on, experiment done, and then they discovered the neutrons later on after Rutherford. But as you can see, is the main thing is in this table here. Rutherford and the later group came in. An atom is made of an empty space. Outside it has a very heavy particles in the middle. They are contributing to the whole mass almost of the atom itself. Correct. So called nucleus, and this inside the nucleus we have two particles. Protons, positive charge, neutrons, no charge, and you can see their mass in 1 AMU. AMU stand for A for atomic, and M for mass, and U for unit. 1 AMU is 1 gram per mole, as you will see later on. That's here. 1 gram per mole is 1 gram per mole, which is more handy here, equal 1 AMU, atomic mass unit. So as you can see, there's the proton and neutron almost identical in mass, almost, not exactly. As you can see, there's a little bit of variation in a very, very tiny after the decimal. So they don't really differ in the whole number, but after the decimal, the fractional differences between protons and neutrons. However, electrons is almost zero, but very, very tiny, 0.000 something. So 9, 3 zeros and 9. So it's a very, very small, tiny. So therefore, it's not considered to have a mass. We'll say almost zero mass, but it does have a charge, -1. When I say zero mass, it does not mean it does not have a mass. It does have a mass. Otherwise, it will not be recognized as a matter. A matter, anything that has a mass and occupies space. It has a volume and mass. But the mass is so minimum, I would say not zero per se, but is at minimum, minimum. Very, very tiny. But it is there. Otherwise, we will not be, recording it. We will not be able to record it, correct? So, and you can see the symbols we discussed last time. And this is the charge of each of those particles. And this is the mass. the mass for the electrons almost zero, which is zero, but we know that's not zero. And the units is for the unit for the protons and neutrons and electrons is AMU, atomic mass unit, which is equal to 1 gram per mole. 1 AMU is 1 gram per mole. So this is 1 equal 1 gram per mole equal 1 AMU. So this is the whole picture of the atom itself. Correct? Now let's put this simple. Any question you have now? Any question you have? Any question? No question? Okay, let's look at the periodic table up in front of you there on the wall. And if you look at this, and we want to see how we recognize those, I mean, the atomic number, atomic mass, and the symbol. So we talked about the symbol, correct? If I will take any of those, suppose I have to look the chlorine here, the symbol here, that's a capital C, capital, and this is small l, and this is a symbol here. This is a symbol here for chlorine element. Chlorine, 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 as an element, non-metal, and it has, if you look at the top, the number, small number says 17. The lower number says, if you look at this one here, it's 35. I would say rounding it 35.5. 35.5 AMU. So I'll take this one here everybody's following here. I'm taking this information here out of this picture, but at least later on. But this is what we are recognizing an element with the symbol, 2 alphabets or 1 alphabet. The first alphabet has to be capital, and this in the top, the small number here, that's in your periodic table. In the book might be different. In the book might be different. This is the small number here is atomic number, and this is atomic mass. An atomic number, of course, this is atomic number is the unit of it is AMU, because all those are involved electrons and protons and electrons, correct? So they are having the unit of AMU. So that's what we have in the periodic table. So any question you have? Any question you have? Before we go further, I would like to just show you here. We'll come back to this symbol and the atomic number, atomic, and then we'll do some one worksheet at least. So let's take this one out. The Rutherford, he came and he put in his postulate that this is empty. The whole thing is empty space, correct? And this is the nucleus, and the electron can be whatever. So you see here. So the distance. This is the distance. As you later on to see, that's the radius of an atom. So, but as you will see, that's not really true. The definition of radius is a little bit different. But he visualized a very nice thing about the atom. He said, imagine you have a football stadium here. This is stadium, football stadium. And in the center line somewhere here, I don't know where the center line is this, but here in the center line here, a small tiny particle like rock or small tiny, it looks like a grapes to me, but I don't know. It's a small tiny particle here. But in his postulate, he does not say particle. He said a mosquito. There is a mosquito here, an insect in the middle line of this stadium. This mosquito here represents the nucleus, correct? Nucleus. And the spectators somewhere here, see some around, those spectators watching, those are he called them electrons, and that's really very nice, a very nice type of bringing the picture of the periodic tables. So he brought to us a very nice picture about how you visualize the so how you can visualize the periodic table. So as I said, the spectators are electrons surrounding this middle line, and the middle line is a mosquito sitting. Can you see a mosquito? No, you cannot see a mosquito in the middle line while you are even watching from outside. You cannot. Can you? No. So it's so tiny, and that's the whole weight, the whole mass of an atom is in the center. That's the center of the mass here. The nucleus is the center of a mass, center of atomic mass. So you get the idea about how you can visualize an atom, very, very tiny unit of the matter itself. So that's a Rutherford, and later on we'll see the radius. What do you mean by radius? It's not really distance of electrons. This is we cannot call this radius because that's obsolete. The definition. Why? Because it is very difficult to localize electron. You cannot measure the electrons here. I can measure the distance from the nucleus. You cannot do that. It's very hard. It's not because the idea is to have localized electrons. That's not. They are moving around the nucleus with the speed of light. And if somebody wants to go in you hear the movie about Honey, I Shrunk the Kids, correct? Imagine you are squeeze your body to small tiny body that fits small tiny super tiny submarine, and you are going through an atom itself. What you will see, you will go through all the stuff you will not see, only dark in your submarine, small tiny super tiny submarine. Nothing there. You will move around and move around and move around. You will see nothing, dark. However, you will see hissing, like a hive of bees. A lot of bees are at their work in their hive making honey, and you will hear something. That's the speed of light. Those electrons are moving, but you cannot see them. Can you see the electrons? No, you cannot see them because they are moving with the speed of light. And our body is not designed to move with the speed of light. The speed of sound, yes, but speed of light is almost impossible because our body will be broken in small pieces. The heat is generated is too much for our body to have it there. So therefore, you can see it, you can visualize. So you are moving around. The only thing your submarine detectors on radar, they give you just the sound of those let's see, of those those moving with speed light, those electrons. But all of a sudden you move with your submarine and then you hit something, your submarine is bouncing back to you. It's a big rock. That is at the center of the very dark. And that's like a universe. If you go out with a missile out or a rocket or shuttle outside, you will not see nothing. Everything dark. No oxygen, no nothing. Correct? Nothing. Everything dark. It's like an atom. You will hit only meteoroids, or you hit stars, or or something like this, or whatever junk inside the space. But anyway, so that's what's happened. That's what you when you hit this, that will be the nucleus. That will be enough. The collision will be enough to bounce you back out of your position. You have to go back because the whole mass of this space in the middle, and this is called nucleus. Can you visualize this? You saw the movie, correct? With his kids. So you can shrink yourself in that. You can imagine shrink yourself, then visualize as you are in a submarine. You and submarine has shrunk to the small pieces, so you can go through an atom and see what the atom is made of. So that's enough for this uh, pictures here. So we'll go for the real periodic table. So as I said, the periodic table will give you the information about the symbol of the atom. This is Cl, 17 and 35.5. Two numbers. One small number, this is always the smallest. That's always the biggest. Okay, guys, this called here the 17 called atomic number. This called here atomic mass or mass number, either or. So all those units of them is AMU. The unit of this AMU, all of those AMU. Correct? So this one here as AMU, atomic mass unit, and this here as atomic mass unit as a unit, correct? Which is 1 gram per mole. So, and this is the symbol. So that's all the information from periodic table. And we said each group will contain elements that behave physically and chemically almost similar. So they have similar physical and chemical properties. So if I look at group 1A, group A, called 1A, starting with not the hydrogen. Hydrogen is non-metal, starting with lithium and go all the way to francium. This type of group here will show similar physical and chemical properties. So you can see is properties here. You can see within the group you have identical properties or similar properties. Within the period we don't have similar properties. So within, let's put this one here. Within a group in periodic table, similar properties are similar, and within a group here, within a period in periodic table, not similar. This is very important to know. This is very important. So if I look, I want to know what's the, they have to be the same. They have to be all of them non-metals or all of them metals. So you cannot say this element are the same, correct? Boron is like aluminum. No, boron is not a metalloid. And aluminum is what? Aluminum is metal. So, but they have to have the same. So from lithium to francium, group number 1A, those all are metals, and they have same behavior physically and chemically. So that's what it says. So this is about the symbol. Now, what is atomic number and what is atomic mass? Atomic number is number of the protons equal number of electrons. What is atomic mass? Actually, we have to include atomic of electrons, but since it's small, atomic mass is a number of protons plus number of neutrons. We stop here. We can add electrons, but since they are almost zero, almost so tiny, we cannot include them. So we just protons plus neutrons will give me atomic mass or mass number. Protons equal electrons, and this is because you have a neutral what? In the periodic table, there's no charge on the elements, correct? Neutral elements. So neutral elements. That's really true. Okay, neutral elements. Here, whether neutral or not neutral, the atomic, because that's inside nucleus, we don't have any change. So neutral or not, protons plus neutrons will give us what? Will give us atomic mass. The neutrons has no mass. Has a mass but no charge, and the protons, they have positive charge. So can I take this one out? Can I take this one out? Let's do this one here. Now let's do this. I have chlorine 17, 35.5, the atomic mass. So I say number of electrons, how much? Number of the protons, how much? Number of neutrons, how much? So I have to come up with the number here. So, well, since this is 17, atomic number is equal number of the protons, equal number of what? Electrons, correct? Correct, guys? So this is 17, this is 17. The protons, P plus, equal E minus. This is a neutral. There is no charge on the chlorine. There is no charge on the chlorine. And now the neutron, well, the atomic mass is 35.5. This one here, those particles cannot be divided. They have no fraction. We have to round 5 and above as 1. This is 5. So this is 36. Rounded to whole number. It has to be what? Rounded to whole number here. There is no half of those units of electron proton. There are no fraction of them, correct? It can't be. If they are making our bodies, those electrons, protons, and neutrons, and we are not fractional, so they should be the whole units. It's the same thing. So 36, which is number of the protons and number of the neutrons. Well, I don't know the number, so we said number of the protons is B plus number of neutrons I don't know. Correct? So now 36 minus 17 will give you what? Number of neutrons. And how much is it? How much is it? 19. So 19 is the neutrons. So let's do the worksheets. Let's see if we can make a worksheet here. Let me first. Everybody has this? Everybody has this? Everybody has this? Okay, so let's take this one out and look at the one of the worksheets here. So trying to get one. It says, well, this worksheet I don't like, but inside the ones you have here, see here, those here, the red ones. You can see all those here. with the number, the symbol, the number of the neutrons, protons, and electrons. Now, before we go further, you can pick up any elements you like of your choice. We'll determine what's the number of the protons, electrons, and neutrons. Pick up any elements you like. Any elements you like? Any elements? Which one? Chromium, Cr? Okay, chromium. Okay. So chromium, I mean, you can look at the examples here. Chromium here has atomic number in the top. Atomic number is what? 24. Atomic mass is the biggest number. How much is it? 51 point what? 51 point what? 51.9 and what? Write it the whole thing, 50.9. So I said there is no fraction when it comes to a number of neutrons. So this is 52, correct? This is 52. So now, number of the protons, how much? 24. Number of, this is the top, atomic number. Number of electrons here? 24, no change. So those are no change, correct? How about number of neutrons? Well, it turns out atomic mass is 52, rounded to whole number, 5 and above is rounded, minus 24 will be what? 8, 2, correct? 28. Is this following? Straightforward? Now let's challenge you in something else. Let's do some challenge here a little bit. Can I take this one out? Everybody has it? Okay, let's challenge ourselves here, and then I'll challenge you with the small, tiny one here. By the way, there is 2 types of writing of these symbols in the periodic table, and in the textbooks or eBooks. So different. We write it. This is very confusing. I don't know why, but I think just for the convenience, I have no idea why. If I have, for example, Al, what is this? What's the name of this element? Al. Atomic number is 13. Atomic mass is 26.9. What? 96. 98 or 98. So this is the periodic table writing. However, the textbook will tell you aluminum, correct? 13 at the bottom and 26.98 at the top. So this way here and this way here, don't confuse yourself with the writing. The biggest number, the main thing is the biggest number. The biggest number is atomic mass, and the smallest one atomic number or atomic number, atomic number, yeah, and the other one atomic mass or mass number. So that's the way of writing it. So I'm going with the periodic table. You have it there. So that's what we are going for. So it does not really matter whatever we are looking at. This is the same thing. So let's take from this one here. I have to know number of electrons, number of protons, number of neutrons. So you tell me about this aluminum. So then, because I chose aluminum because it has large charges. So how many? 13. How many? How many? I have to round this one here because this is 5, above 5, correct? 5 and above. This is how much? Minus 13 is how many? 14. So that's what you have here. Everybody agrees? Everybody is following? Everybody is following? So now here's the challenge. You tell me whenever you are ready. You have it? Everybody has it? Okay, good, good. Thank you. So let me take this one here and say, how about not taking everything, I'm just keeping everything as is here. I'm switching here, saying, no, I'm not like AL to be neutral. Because AL, I know it's understood is neutral because there's no charge. When it's no charge, that means 0. So this is 0. Now I said to myself, yeah, that's neutral. And that's what I had here, 13, 13, and 14. Correct, guys? That's what I had when they are all equal. Now I'm challenging myself. I don't see this is neutral here. How about if I have AL 3 plus positive charge? What is the number of electrons, protons, and neutrons? So can we answer this question together? Yes, no? Yes, we can. That's good. So let's take this one out and then we'll see how about this aluminum 3 plus. What are those numbers inside? So can I take this one out? It has it. So let's take this one out and look at the charge, not neutral element, the charge element. We have Al, nothing changed. This 13 will be remaining as is. Correct? Nothing changed. That's in periodic table. They show the neutral, no charge on them. But even if the charge, that will remain 26.98 as is, and this is 3 plus. So it turns out to be when I have positive charge, it has a meaning for that. Means element or element, let's make it one, element here, donates its electrons. So, and the number of electron donated, the number is equal number of charge. Okay, so meaning I have number of protons. We said there's no change of them, correct? No change at all. So that will be what? How much is it? 13. There's no change. Those are inside the nucleus, hidden deep inside the nucleus. No changing. Nobody can touch them. So, okay, guys. However, we have now a charged element, not a neutral one. It has a charge and positive charge. Positive charge means it has lost. So aluminum had or has lost, present, has lost 3 electrons. Are this following? When I say 3 plus, the plus means losing. How much? Number of the charge, 3. Plus how many? 3. So, number of electrons now, 13 minus how much? 3. How much they are? 10. Perfect. Makes sense? When it comes to the neutron will tell you, I don't care. I'm inside the nucleus. I have nothing to do with the chemical reaction outside, in and out, donating and accepting, or losing or gaining those electrons. So, say, well, this is 26.98, 27, minus my my protons, not electrons, protons. This is 14. So it looks like inside the nucleus is not touched. The number of electrons and neutrons and protons are the same, are not touched. The only thing, because the charge is give you the hint, this is you are losing or gaining those electrons. So this one here, the charge is what is 3 positive, correct? Now let's take the negative one. How about that? Let's take what? The negative one. Can I take further another page? Another page? Okay, let's take another page. Let's take the silver here, 2 minus as a charge. Phosphorus is 3 minus. So I need from you here to tell me number of electrons, number of protons, and number of neutrons. Here's the same thing. Number of electrons, negative here, negative. Number of the protons, number of neutrons. Now, since we are saying this is negative here, means you are gaining those electrons because they are negative. So when negative means you are gaining extra. So negative means gaining electrons, negative charges. By how much? By the number of the charge itself. Number of the charge. Okay, so now let's look at sulfur here. Let's look at sulfur. It says in the periodic table, not in the book, 16 atomic number and 32, not 32, but it's 31, 32.05, 32.05 here. Okay, guys, here it is. 3205. So now you tell me about the electrons. About the electrons here. How many protons we have? That's easy, correct? How much? 16. How many neutrons? 32. This is 0 here, and that's 0, correct? So 32 minus 16 is how much? 16. So neutrons are 16 here, and the protons are 16. Okay, how about the electrons? That's a problem, electrons. We have 16 here. Since we have negative charge here, we have to do what? So here it is. So electrons, that's a problem here. Always, as I said, it's not changing. The number of atomic mass or mass number is not changing. So this one is equal to, and this one will be 16. Minus or plus? Plus. This time is plus 2. So how many? 18. So this one here, 18. So you get the idea? Okay, so here is negative. Remember, negative. You have to add. Add. How much? Add 3. Correct? Negative, add 3. So the protons are straightforward. Look at the phosphorus. Phosphorus is 15 here, atomic number, and it has 30.97. So 30.97. Correct, guys? So number of the protons, how much? 15. Number of neutrons, how much? Around this one here is, so 31 minus 15 is 16, correct? Now the electron is a problem, but not a big problem for us, because this negative means I have to add. So the 15 is the number of the protons and number of electrons in the neutron one, that's 15. I have to add because you have a negative charge here. Negative charge, I have to add how much? 3. So this is 18. Everybody got the idea? Okay, good. So that's That's at least will cover up this area. Whenever we have elements inside the periodic table, neutral, or if they can be positive charge or negative charge. And for saying in general, the metals are always positive charge, and the non-metal are always negative charge. That's the general rule. I will write the rule here. Hold on, hold on. Can I take this one out? Can I take it out first? Yes. Negative charge, you have to add the number of the charges. If you have, if you have positive, you have to subtract. So let me write the general rule. I just say it here. The general rule here, guys, look. General rule, that's general rule. Metals are always positive charge, or they have positive charge. The metalloids can have either or, positive or negative charges. The non-metals, the non-metals have positive or negative charges. Depends, correct? But majority of non-metals have what? Negative charges. So the metalloids, because they have always the characteristics of metal, non-metal, they can swap their charges, correct? Metals, no exception. All the metals can be what? Cannot be negative. Metals, they have to be positive, always. Very important. The metalloids, they can swap because they have both character of the metal or non-metal. They can act chemically both ways. The non-metal, the majority is non-metal. However, we do have sometimes, correct, they can be positive. Everybody is following? I can give you in a compound, especially in a compound here. In a compound, we just took this one here, correct? I'll show you as a metal here in a compound. So everybody has this one here. Everybody has this. Everybody has this. Okay, so I can show you just we went through an example here, which is very important. We had this one here, chlorine, correct? We said 17 and 35.5. Now this is negative. We can determine the both of these. However, in some instance we have chlorine positive, so the majority of nonmetals are negative, but sometimes that's in a chemical compound, in a chemical compound. So in a chemical compound, they might be positive. So now we'll do for me those three. Electrons, number of electrons, correct? Oops, sorry. It took it out very quickly, so. And number of protons, number of neutrons. Negative, and here is number of electrons, number of protons. This is wrong here. Negative Okay, guys, can somebody will help me with this, please? Somebody here? So let's start. Let's give it another color, maybe brown. So number of electrons here, how much? Well, let's start electron at the end. Number of proton, how much? Neutron, how much? 36, because we rounded 5 and above, 36. Minus 17 is, we said what? 19, correct? How about here? Number of the protons? 17 does not change. Number of neutrons? 5. 36 minus 17. As you can see from here, this results here, those results here means nucleus has nothing to do with charges. Are you following me here? Nucleus, the nucleus here, whatever the particles inside the nucleus, they have nothing to do with charges, positive or negative, correct? On the element itself. So now the electrons is the problem here, correct? The number of electrons here, we have 17, correct? And here we have 17. However, is when I have positive, I have to do what here? Subtract. If I have here negative, I have to what? Add. How much? Is 1, because 1 is understood, not written, correct? It's 1 charge. There's no 2 or 3, or when I put just a charge by itself, is 1. And 1 here, in this case, understood, not written. Understood, not written. Not written here. Okay, plus 1, and this minus 1. So plus 1, how much? 18. And minus 1 is 16. So that will end up with this charges on the elements. So everybody is following me here? Okay, good. So let's take this one out and see how far we are with the yeah. Now we'll go for something called isotopes and atomic weight. So what do we mean by isotope and what we mean by atomic weight? So it turns out to be, I'll take another page here. So we have to define isotopes, and then we'll come back and look at the atomic weight. So an isotopes usually is happen most of the time naturally, as the element will be found in nature with different modification, correct? An element is found in nature with different modifications due to different number of neutrons inside the nucleus. So for example, we have carbon. Carbon has itself 3 modifications. We have carbon, we have 3 isotopes or modifications in nature. So those isotopes is, we say carbon dash 13, that's the way you write isotope, carbon dash 14, and the biggest one, carbon-12. So this is by far is the most abundant one. So we have carbon has 3 isotopes. Isotope without the, can write it without isotopes. Without. Okay, so isotopes C without E, isotopes. We have 3 modification or 3 isotopes on an element because carbon found in nature, it has 3 different modifications, 3 isotopes because of course this is by the way if I this is the atomic mass, and dash, that's the way, this is a dash or a hyphen, and this is capital, that's the symbol of the element, element symbol here. This way we can write an isotope. Isotope is written, the symbol of an isotope. So when I write this one here, this is an element, correct? But when I write it, this one here, this is not no longer element, this is isotope. Okay, guys, so we have to differentiate between up to potassium, I think, up to the potassium 19, atomic number 19. Those are those elements can be found, found in nature without without any without any force to be having isotopes. So, but they have an isotope naturally. So they have an isotope. But the other one, the other element, radioactivity, that's what you say, radioactivity. So the other ones you can force them to have isotopes. So, but anyway, elements in general, they do have different modification in nature and or in the lab. So you can produce those isotopes in the lab as well. So carbon has 3, carbon 12, carbon 13, carbon 14. So let's look at the number of again. We look at the number of protons, neutrons, and electrons. We see they're different neutrons, correct? So let's look at this. Can I take this one out? Can I take this one out? So we'll make a small tiny table. We'll say this is an isotope here. So this is an element here first. Element. Correct? By itself. Now out of this element here we'll have C12, C13, and this is isotope. C13 and C14. So we need from this one here, back again to the same problem we had, number of electrons, number of protons, and number of neutrons. Well, it turns out to be for the element there, carbon, if you look at the carbon, carbon is 6 atomic number, and it has 12, correct? 12.6 or 12.0. Okay, 02. Yeah, so 12.02. So that's an element here. This is an element here. So regardless of because it's not charged, the number of the protons is not charged. There is no charge on them. There's no gaining or losing, correct? So number of the proton, atomic number is number of the protons equal number of electrons. So how many is this? 6. How many is 13? 6. How many is electrons? 6. How many protons? 6. 6, 6. So it looks like all the isotopes will not differ in electrons or the protons. They are the same. They are the same, no changes. However, we have here, correct, number of neutrons. Well, look at this number of neutrons. So how much is number of neutrons? Here we round this one here to how much? 12, correct? So this is 12 minus number of the protons is 6. How much is it? 6. We have 6 neutrons, correct? Here we have still the same thing, 12 minus, correct? However, this is what I said. This is the atomic mass here. We are not going by this here, by the element. We are going by, those are atomic masses. Atomic mass. This is atomic mass, and this is atomic mass. So this one here is, how much is it now? It's 13. And this one, the other one, is 14. Those are here, 14, 13, 12. Those are the atomic mass we are using. And the number of protons is not changing, 6, 6. So this one will be 7, correct? This one will be 8. So, and that's really true about the isotopes. The isotopes of an element, those, they don't differ in their electrons number or their protons number. They differ in their what? Neutron number. So 6, 7, 8. And you can look at the chart or table in the, you can Google it, and you'll see some elements, they have 5 isotopes, some elements have 8, some elements 10, 15. So it depends on the element itself. But this way we can determine the protons, electrons, and neutrons of an isotope. The main thing here, we have to concentrate ourselves on the dash, means that's the atomic mass. So atomic mass, those atomic masses. And then you use whatever you have, atomic number, correct? Atomic mass, and here's atomic number. So atomic number. And every time you get what? Different number of neutrons. Those are remaining the same thing, no change. See here? Protons and electrons, they don't change. They remain the same thing. Correct, guys? Correct? Everybody's following? So can we take this one out? So that's what the isotopes. Now, the next step is to look at the average atomic weight. Why most of the elements, they do fractional atomic masses, as you see, 12.02, 35.5. Why these atomic masses, they have fraction? Although we know that electrons and then protons and neutrons, they are whole unit. They are not fractional. They are not fractional. Can I take this one out? Can I take this one out? Okay, let's take this one out. Okay, the question to us here all: why do elements in the periodic table have fractional values of atomic masses? That's a good question here. Well, the answer for this is, that's the question here. The answer is, the elements inside the periodic table have, so let's do another color. They have a fractional atomic, well, the we'll say just here, the fractional atomic masses appear in periodic table due to the natural abundance of each isotope of each element of the elements. Yeah, let's put it of the element. This of the element. We'll do some examples, of course. Okay, guys. So let's do an example here. Let's do an example. Everybody has it? Everybody has it? Okay, so we answered the question here. Why do the whole elements here, not whole, the majority, over 90%, they have fractional atomic masses? Well, it has to do with their abundance in nature, right? And abundance, and then you can add here abundance in nature. Okay, guys. So can I take this one out? Take it out. Okay, let's take out and look at the for carbon isotopes abundance, carbon isotopes, and their abundance. So guys, okay, it is carbon-12 98.9, correct? So here it is, and I'll take a snapshot of this. You do have 1 minute, guys. Cool yourself down. You do have 1 minute. So here it is, and we have, guys, here it is. We'll come back. We'll go and look at this together. So we have. I'm saving this one here for next time. Here, guys. So if you look at this, you have this. So let me see here, guys. Listen. Carbon-12 has abundance of 98.89. I'll stop, but I will just write this one here for next Wednesday. Carbon-13 has abundance of 1.110, and carbon-14 has abundance of 0.00%. When we come later on, this Wednesday, we'll look into those abundance. So this is the natural abundance, and this is called natural, found in nature. Okay, so we'll come back and come back and look into that this coming Wednesday. Thank you.